Hmm. All right. So before we start, there was a question like, how is the AI course compared to machine learning? So I thought we are now at a stage where we could give you a broad overview of how the courses in Auburn are organized in terms of like basic, advanced, basic AI, then mid-level AI, and advanced AI. So this is kind of like an overall structure that I kind of see myself for AI. And if you think about the first course, AI, like that's kind of the intro to all of this. So it's like an introduction course, and artificial intelligence itself is pretty broad. Anything that has to make a machine intelligent can be called AI. And then machine learning seems to be a popular way to do AI, but it kind of like has replaced everything else in AI. So that's why you keep hearing a lot about machine learning and all, but it's not the entire AI kind of umbrella, right? And so this is more like from a method perspective, like what kind of models, one particular area of models that are very popular for doing AI. This is more from the data perspective, like, okay, assuming that, because it's not just the model, it's also the data, and how you deal with the data, how you process the data, how you interpret the data. So if you put so it's like a perspective. You have this whole AI goal, you can put more like you can zoom into the model more and try to focus there, or you could also, given a model, you could focus into the data. So that part is data mining. So it's more about data. There is a lot of overlap between them because, of course, all of them are AI, but they just have different focuses, okay? And then at the advanced level, there are courses like information retrieval that basically talks about search engines. So it's also about data, but more about unstructured data. How do you find information from unstructured data? There is courses like bioinformatics where you have exactly biological data, and you are looking into biological things. You are trying to do AI with some models and biological data. So that's bioinformatics. That's kind of the advanced level. From the model perspective, if you go at a higher level, so deep learning has been a big thing because everybody is doing neural networks. And even further, if you go like even more advanced, there is reinforcement learning that people are talking a lot. Right now, it's just more about being fancy rather than it actually works. Some cases it works. A lot of cases it's just theoretical model and it doesn't really work in real life, and people are working on it. This is an active research area. So that's not, I mean, there is a course in EC department you are very interested. If you are, then reinforcement learning is another option. Deep learning is all about neural networks, transformers, everything. Then you have NLP. That is more about language, sequence modeling. So how do you model sequence data, right? And there is computer vision, where you are basically doing image, video, this kind of modeling. So Both of them are heavily dominated by deep learning, but yeah, so they are more applied areas of machine learning. So who teaches these courses right now? So AI is something that Satya is teaching this semester. I'll be teaching next semester. This is something that is taught always by Yang Zhu. Do you know him? Okay. Machine learning, Ang has been teaching this. There was a faculty called Bo Liu who used to teach this, but he's no longer here. So that's machine learning. Information retrieval is just me. Bioinformatics, how many of you know Heinz Eaton? Heinz? No? Okay, Heinz is one. And then we have new faculty Ting. So both of them are experts in bioinformatics, so they are probably going to offer something if you're interested in that. So the special topics course you see under their name, ask them whether this is bioinformatics or not, if you are interested. This is taught in ECE, not in our department right now. Deep learning is Ang so far. NLP is me. Computer vision, I think this is Satya. And there is a new faculty called Pan He. Probably they are going to offer something like this. You can reach out to them to ask them because they are the experts there. So that's kind of like what our department has to offer. We didn't have so many faculties like even like 3 years ago. So now it's a great time. If you're interested in machine learning AI, you have a lot of experts and resources. Just go for it. Any question on this? If you have found machine learning pretty okay, not so tough, then probably doing AI will not help a lot. I would suggest go for more advanced. But if you struggled a lot in AI, machine learning, probably you want to go back to the AI course just to do a reinforcement of your understanding, okay? Just the basic level, high level kind of thing, okay? Okay, so in the last class, we were talking about artificial neural networks. And we said like it's basically a network. And a network is just a graph. And how many of you had discrete structure or data structure course? How many of you have never done data structure? Then what about the rest? I mean, data structure, one big part of data structure lecture involves like graphs, right? How do you search over graphs? What are the nodes and edges and everything? So a network is essentially a graph. But here, rather than data flowing over the graph, there is also learning happening in these graphs. So these are network learning techniques where you kind of iterate over these graphs to learn some weights to do some task intelligently. Okay? So essentially, we are talking about some units, some nodes in the graph that are connected in some fashion and that collectively can do some intelligent task. So all you have to do is to define the architecture of the graph or the network, which is essentially some nodes, some units, and what kind of connections they have. And that's it. And then you basically need to do one last thing, is the connections they have, what does that connection look like? So we do that in terms of weights, network weights. So each edge has some weights assigned to it. And that is what we need to learn. So when we talk about deep learning, neural network, learning everything, all it is trying to do is that network, which consists of some nodes and edges, it's trying to learn the weights of those edges. That's it. When people say, okay, I have got the GPT embeddings or GPT weights downloaded, that basically means there is a huge network and called GPT, and the weights of that network has been already trained, pre-trained, and saved. So that saved set of weights you download and you can reload in your machine. That basically means you have already a pre-trained model. And those networks are massive. We are not going to talk about like those massive models in this course, but we'll talk about the basic fundamental neural networks. And then again, it's just about size. The same ideas hold in those like massive models, what we call today like large language models, generative AI models, whatever. You name it. It's the same basic thing. And more surprising part is this fancy neural network that you probably have been imagining, like you are very interested to know about. It's, as I said, like it's kind of maybe a little frustrating to you to know it's just a graph with some units, but the units are already something that you already know. Maybe the unit is just a dot product. It's just a connection of dot products. Not that fancy anymore, right? Okay. So, first of all, we have a feature space, right? We talked about this. Neural network is all about layers, right? So you have layers, and we said like there are three kinds of layers. One is the input layer, right? Then we had hidden layers, and we could have multiple. And there is output layer. Right? Okay. And there will be some units in the hidden layer as well. And there will be some output neurons, right? And then you define connections, right? You connect. The simplest one is everybody in one layer connects to everybody in the next layer. So it's kind of like this, dot, dot, dot. Right? So you're essentially connecting some processing unit in a big network and hoping that network will solve your problem. Right? Now, previously we said like we had a different formulation for classification task and a different formulation for regression task, right? But now we are going to just have one formulation for both tasks, which is essentially the mean squared loss. So what we are saying is we are going to, so the network is going to predict something, right? This output layer is going to give you some prediction. And all we are trying to do through these weights is to learn an unknown function. That's the goal of machine learning. Given the data x and the output y, learn a function that maps x to y. And that function, f, is nothing but this collection of weights, all these weights. Right? So now this function is trying to map x to y. Once you learn this mapping, let's say you learn it, then this function of w, which also takes, actually this notation is probably not the right notation. What we should be writing is kind of f of w with respect to input of x, right? So with respect to the weights w, this function maps x to y, but it may not be always correct. So the function of w of x could be different from y, but we want that difference to be as minimal as possible. right? That is our learning objective. We don't, if this is always equal to y, then we have a perfect learning, right? That doesn't happen most of the time. And initially, with random weights, we'll not have something like this, where this is 0. But our goal is to minimize this squared loss. And the obvious question is y square? You probably know the answer by now, right? What is that? It's convex. It's easy. Square functions are easier to optimize. We can do efficiently gradient descent on them. So our objective function is to just look at the output, what is coming out of the output layer, and match that against the ground truth, the actual labels. Now you have a slightly different notation here, right? So they are saying it's xd and it's a td. It doesn't matter. And they are doing it for all the instance, right? So this is like over all the examples in your testing data set. So this td is just your y, the label. And xd is your data. And you are going over all the examples of your testing data to minimize this loss. But this, you are not doing that on the testing data because you will be training on a training partition. That's your learning objective, and then try to test it on the testing data, right? So this is your learning objective. Over your data set, training data set, you want to minimize this squared loss. Now the question is, okay, that makes sense for regression. That's what we did actually for linear regression, right? We saw that. But how does that help for classification? Well, it's not probably the best function for classification, but still you can do something. For example, let's say your actual label is 0, but you predicted 1. Still you get a loss, right? 1 minus 0 is 1 squared. That's a loss. But if you predict 0 and your actual label is 0, then you have a 0 loss. That can still work. This is, although this is not the best function to approximate, to have a loss function for classification, and there are many other variants of loss functions, but for generality, we will go in depth with this one because this is simple. This is kind of, it can handle both of them. Not maybe very, like, it is well suited for regression, not super suited for classification, but still that does something for classification as well. But then there are alternative loss functions that we can think of in terms of classification error. And there are methods, and we will see if we have time to cover them. But right now, let's focus on this mean squared loss, which can be used for both classification and regression. Any question? Is the goal clear? Okay. Okay, so let me ask you some questions. Do we know x? Do we know y's? Okay. Do we know how many nodes how many units we want to have in the input layer? Right, because x defines that. Whatever the dimension is of x, that is the number of units you want to have. That's the number of inputs. Okay, do we know how many we want in the hidden layer? No. Do we know how many we want in the output layer? Assume a classification task. We know. The number of classes are there, you just have that many outputs. Whatever fires, that's your output, right? So we don't know basically the input, the hidden layer, and we'll just assume that we'll have something that, let's say x is 1000 dimension, our y is 3 dimension. So hidden layer, we can think something in between, let's say 100. It could be 200. It could be actually more than 1000. It doesn't matter. All I'm saying is this is something. And this is a hyperparameter. This is the architecture we are talking about. And there could be different network architectures, right? This is just one architecture. With 100, you get one architecture. With 1000, you get another architecture. But then the point is mapping 1000 to 1000 dimension is probably not that helpful. It may be, we don't know. Maybe we want a more like denser representation that can capture higher level features. And whatever is happening in these hidden layers are not even interpretable. That's the point, right? What it's going to do. What feature is going to be captured in these hidden layers, we don't even ourselves know. That is what the machine will learn in real time, in the learning process. So there is no clear answer like what should be the best number of units. And even how many layers you actually want, because you can have more. There is no straightforward answer. Depends on your complexity of task. For different data sets, people have shown different kind of networks work well. Okay? There are some general guidelines, but there is no absolute science here. Okay? All right. So let's say we just fix some arbitrary number of, a particular number of hidden layers, right? Then do we know how many edges we are talking about in the whole network? Let's say one hidden layer, one input layer, one output layer, and every node in one layer connects to all the nodes in the previous layer. Now, can we know how many weights we are talking about in this network? Can we? Yes or no? Yes, because we already know, right? So here, if you have D dimension, if you have H dimension, and if you have 3 dimension, we are essentially talking about D times H times 3 like different weights, right? That we need to learn. But you can easily see, not necessary, right? Maybe I'm wrong. So D times H is here, and you are learning H times 3, right? Plus. That's the right formula, right? So the whole point is you kind of can come up with a formula, and you know what weights you actually have to learn. For each weight, you need to learn what this weight should be for these ages, like every age. That you need to know. So before we can know what that age looks like, even before that, what do we need to know? In a graph, before defining what the age means, what do we define? The nodes. I mean, if I don't know what the two nodes are, what does the age even tell you, right? So in the input layer, we know what this means. In the output layer, we know. But in the hidden layer, do we know what this node looks like yet? No. So what can we do? Let's think about the simplest thing to combine features. Let's say I have this D-dimensional feature. I will combine them in this unit in some way. What is the simplest thing? We will try to combine these D features through these D different weights in some way. What is the simplest thing? Dot product. Yeah? Because you have W1, W2, W3, W4, W5, and you have X1, 2, 3, 4, 5. So you essentially take a dot product over Wi, Xi. Right? Forget about how we figured this out right now. Let's say you know some W. Okay? You can take a dot product here and combine those features. Is that okay? Now, think about the second one. What can we do there? The same exact thing with the same weights? No weights. No, new weights. New weights, yes. So probably another dot product. Another dot product with a new set of weights. And we can have different set of dot products. Now think about in perceptron, we just had one dot product, right? Now instead of one dot product, you could have many different dot product combinations at the same time and try to combine those dot products. So now this dot product itself becomes your feature, and you create multiple different dot products, not X anymore. These are more complex features. And these dot products, then again, you combine them some other way maybe in the output layer, and you keep doing this. So now you are essentially creating, because this unit with a different weight will have a different dot product than this one. So every unit is going to learn something different. And these different things will try to create more complex features. And based on those complex features, depending on the complexity of your goal task, you will be able to do better as you go deeper. And deep learning is nothing but a deep neural network that has many, many different layers. There is nothing else going on there. It's kind of, the super fancy stuff is kind of actually boring if you really think about what is going on inside. Okay. Good. So now, the ultimate question is, if we decide on the architecture, if we decide on all the edges that we have, what is essentially that we need to learn? What is remaining that we don't know? What do we don't know? Yeah, we also don't know them. We just assume that we know them, but we actually don't know these layers as well, right? Do we? No, we just know these inputs. What is going input here in these input layers? We don't know any of the weights, right? And the weights are complex because now they're connected in a network. So let's simplify this, and let's think about just one unit. How can we learn that? And we will go from there, right? So in terms of the unit, we talked about each unit could be a dot product, right? What is the problem with that if we just do dot product everywhere? Let's say we'll just do dot product for every unit other than the input layer. Yes. What is wrong? Lot of compute. What else? Yes.
Everything is linear.
Everything is linear. Dot product is a linear function. You're essentially, it's like a plane that you are multiplying, right? So remember, if you have a dot product with respect to wi xi and another dot product which is wj xi, if you sum them up, they are again a dot product. They are again a linear combination. So you are essentially creating many, many linear combinations, and then again taking their linear combination is just again another linear combination. So if you have a nonlinear problem, would dot product work? How many of you think that it will work? How many of you don't think it will work? Okay, it will not. Then what else can we do? So this unit, just dot product is not going to help. What else can we use? Try to bring in ideas from this course, whatever you have learned so far.
Kernel trick.
Kernel trick. But kernel trick on what? On the dot product?
Yeah.
Do you have two different points here? You have a set of weight and a point, right? You need an alternative formulation for that. Yes.
Wrap it in something nonlinear.
Some nonlinear unit. Yes. What could be a nonlinear unit?
Sigmoid.
Sigmoid. Okay. That's even better. But what could be even simpler? For example, what about this function? This 0, 1 nonlinearity. Step function. We could do that. If the dot product is greater than 0, you put 1. If it is less than 0, you put 0. What is this called actually? That is a perceptron. So you could have, each unit could be a perceptron, right? But what is a problem with perceptrons? Why did we not stick to end with perceptron? What was wrong? They're not differentiable. You cannot differentiate this, right? So what is the closest differentiable function that approximates this? Yeah, what was the function in logistic regression? The sigmoid, right? Softmax is for multiple, and sigmoid is just for binary classes, right? So we did logistic regression with like a smoother function that looks like this. That is differentiable, that is nonlinear, with a bounded probability interpretation. So now we could actually do a logistic regression unit that is differentiable and that is great. So now in multi-layer perceptron, whatever you have in your like project to implement, actually the simplest formula is to just use logistic regression, because now everywhere you have differentiable units that does non-linearity, that is differentiable, that has a probabilistic interpretation. That is excellent. But still we have some challenges, right? And we will see what the challenge is. The challenge is, I mean, we want to learn this network, and we know we love gradient descent. We want to do that. And we have seen how to do gradient descent on logistic regression, right? We have seen that. So what is new here? What is new? What is the challenge? Because we know how to do gradient descent in logistic regression, and we are saying every unit is now a logistic regression. Yes? How it's wrong, okay? Yeah, so let's try to rephrase this question. This is the right question, but I can determine that at the output layer I can, right? Because I know what the output should be in the training data and what this model is throwing out. I know that. So that part is more like what we have already done in logistic regression. I mean, we have seen how to do it. What is the actual challenge? Yes, we don't really know what is happening inside, because it's like a accumulation, it's like a propagation of error that actually resulted in the final layer. So it's a series of actions that happened, and we can only see the final part, and we can only compute the final one. But if I had n different hidden layers in between, I don't know what happened there. That is what we need to figure out. And figuring out that thing is actually called the backpropagation algorithm. So it's not enough to just look at the output layer error and try to correct it. You have to backpropagate that from the very end to the very beginning. Okay? You have to backpropagate all the error so that you can correct all the errors in all the ages that happened through that forward propagation process. Okay? That's what we are going to do. Any questions so far? Okay. So we have already talked about this, but let's see. So let's take a very simple example, right? Think about two different inputs. Okay? Actually, you see 3 here. That one, just consider it as a bias term. Remember those kind of Wx plus b, right? X plus b. And we created an augmented representation by saying we could create a set of weights in this way, and then we could add another weight, and we could take a dot product with x1 to xk and having one appended. That gives you a compact notation of this. Remember? So that one is essentially this one. Okay? So let's say we have just 2 inputs. we have 2 units in the hidden layer. We have 1 output layer, okay? It's a binary classification task, let's say, okay? If it fires, it's a class 1 in the output. If it doesn't fire, it's negative class. Okay. And as I said, if we do dot product, we could do that. We have these weights. We could do dot product in both of them with different weights. And then we again have 2 different weights that we take dot product with these 2 values, v1 and v2. We take a weighted combination of them. And that could be the output. And the problem was, if you take a dot product, you cannot handle nonlinear problem. And classification is definitely not a linear problem. It's just a discretization problem, right? You have fixed set of classes. So this is not going to work, and then because if you take a combination of linear combinations, that is still a linear combination. And we have already said this. Then we talked about this kind of 0-1 loss, which is essentially a perceptron. And if we do a network of perceptron, we will get nonlinearity. That is great. Once we know these weights, we will get nonlinear things, and we'll get a nonlinear 0-1 output. But we don't really know how to learn them because they are not differentiable. So having a network of perceptron is not going to help us. We don't have a differentiable function here. So the closer alternative and the useful alternative is to have this sigmoid function. This is how it looks, right? This is helpful because now you can do differentiation. So remember, sigmoid is nothing but an exponential transformation of the dot product itself, right? Sigmoid is 1 divided by 1 plus, this is the input data, e to the power minus x. Here, this x is essentially that dot product we are talking about. So it's, you take the dot product, but then take a exponential, a sigmoid transformation over that, right? That's using this function. That is what logistic regression does. So now this is useful, and we can backpropagate, and we will try to see how to do this. But the point is, we can do this for the final layer. We just don't know how to do it for the hidden layers, and we need to find a general formulation so that we can learn any weights, not just the output layer weights, not just these 2. That doesn't help. We also need to know all of them. Okay? And backpropagation algorithm helps you do that. Yeah, so that's what we are going to learn. And there is a property that we are going to use, which is sigmoid of x is essentially 1 divided by 1 plus e to the power minus x, right? That's the definition of sigmoid function. And because we are talking about backpropagation and differentiations, so let's see, we need to compute this derivative a lot. So let's first have a simplified form of this, and we will use that again and again, right? So if I do a differentiation of the sigmoid function, what does it look like? What is the differentiation of this? Okay, what is the differentiation of x to the power minus 1?
Break down the -1.
Minus x to the power minus 2, right? Minus x to the power minus 2. Okay, so this should be minus x to the power minus 2, right?
And then you have to drag out the derivative.
And then you have to take apply the chain rule. Also, you need to, because this is a function of x, you also need to apply that on the e to the power minus x, which is essentially minus e to the power minus x, right? Is this clear? Okay. So that means this 2 minus cancels out, right? So now we can divide these 2 terms. One like e to the power minus x once, and the other part is e to the power minus x divided by 1 plus e to the power minus x. Simple decomposition, right? I mean, trivial algebra. Clear? Now, this is actually equal to 1 minus of this, right? Right? Is that clear? So this is essentially this. So we have sigmoid of x and 1 minus sigmoid of x. So the derivative of sigmoid of x is essentially sigmoid of x times 1 minus sigmoid of x. That's what we need to know. So the derivative of a sigmoid function is the function itself multiplied by 1 minus the function itself. Is that clear? Okay. So let's now try to see what is going to be our actual loss function, right? And we are going to obviously do gradient descent, right? So we know what the gradient descent formula looks like. And we had two different versions of gradient that we already learned in many, many different classifiers. One is the batch mode, and the other one is stochastic mode, right? In the batch mode, you compute the gradient over all the examples, average them out, and take a step. In stochastic or incremental process, you take one example, compute the gradient, and go in a suboptimal direction, but there are proofs like if you do it infinite times, you will actually converge with a much better like efficiency, right? So that's the stochastic version. Yes?
And if I remember correctly, you said for the stochastic, you only use like one data point at a time?
Yes, one data point at a time. Yeah. Okay, so whatever that is, but because this is efficient, we will just focus on probably the stochastic version, where you are just looking at one example, and your error function at that example is just this, right? I mean, this half doesn't really matter. It's a constant because we are trying to optimize this. But this half is there because if you take a derivative, there will be a 2 in the front, and we will cancel it out. That's why. This is just a mathematical trick, just to simplify our life. It doesn't mean anything. The actual thing is this square, the square between your actual label and your predicted label. That's what we want to minimize. We want to minimize this function, the difference between your prediction and your actual label squared. Okay? So we want to minimize TD minus OD whole square over all the possible D, right? Over all possible D in the data set, in our training data set. And we just have a half in front just as a trick, constant, doesn't matter for optimization, helps us with some maybe, what does it help with? It helps us write less, save some pen paint, or just in your laptop, one of the pixels don't need to like draw a half or something. So that's what it saves. Okay? But the point is, essentially you have a loss function that looks convex like that, because it's a squared function, right? It should be convex in a that's a three-dimensional kind of representation. So what is essentially happening, so in that space you are looking for a W that will minimize that function there. And you are essentially, this is the space, right? If you think about a 2D space, this is your W1, this is your W2, and in the z-axis you have the error. And that looks like a convex function that has a global optima. You are trying to if that has a global optima, you have to, depending on where you start, you will actually go to that global optima if you are lucky. If you are not, you can get stuck in a local optima that just depends on what this function looks like, right? So in another visualization, this is the same gradient descent in 3D space. You have W1, you have W2, you have that error, and at this point, you see that this is the direction where this loss function goes down. So you, in this 2D space of W, you make a move in this direction, right? So this is the 3D space move, this is the 2D space move, right? That's what gradient descent helps you with. So you compute partial derivatives with respect to each weight, and then you have a direction, gradient direction to go, and you go to that, towards that direction, because you cannot take one derivative because there are multiple weights here, and you have to take partial derivatives with respect to each of the weights to actually define the final direction you want to go, because it's a high dimensional space. Okay? Yeah, and then we will definitely apply chain rules whenever we feel like we need to. But before doing that, let's talk about this objective function. If we try to optimize just for one unit, what would that look like? And then at the output layer, and then how can we use that to compute something in the hidden layer? That's where the actual challenge or trick is, right? So we want to know, how do we compute? All we need to know is, what are these weights? And then what are these weights? And if there are more layers, what are this? We have to back propagate one at a time. And we cannot start here because we have no idea what kind of errors happen here until we see, because only we see output at this layer. So first, you first see what happens with all the random weights you initialize. You throw some example and see what happens. And obviously it will be terrible, but then you can compute how terrible it is. What is the error at this output layer? So let's take one example from here, one unit, and let's see what that looks like. That looks something like this. Just for one example, there is, there is still this all D, because every individual example goes through that layer. Every unit, right? So this is what that looks like. And what we need to do is to compute the derivative of this function, right? Is that clear? Now, TD is your label, that's given. You cannot do anything about it. But OD is your prediction, right? And we are assuming now there is this sigmoid function on the dot product, the logistic regression kind of classic unit that we are using, which is essentially you perform at this layer, you take all the weights here with all the values that has been forwarded, take a dot product, and then take a sigmoid transformation of that, right? That is what each unit will do in our neural network. So this OD is essentially a sigmoid transformation of WIXI. And it's a summation, it's the dot product, right? Yeah. So this OD at the output layer is just combining. Now just think about, there is one input layer, right? And one output unit. We are just imagining this simple scenario. So in this case, the figure that you see on the top, we'll just do a dot product and then take a sigmoid transformation of that function, and that is our OD, right? And they have simplified the notation of this dot product by saying this is the net contribution of the input D on that particular unit. So net D is nothing but the dot product of D in that with respect to that W. It's the same dot product, the net D. Okay? We are just replacing dot product with net D just to simplify our notation. But because this is a sigmoid function, now we know what is the differentiation of this, right? We just calculated a while ago. What is the differentiation of a sigmoid function? What is the differentiation of sigmoid? Let's do sigmoid. Sigmoid of x. What did we derive?
Sigmoid times 1 minus sigmoid.
Sigmoid times 1 minus sigmoid, right? Good. So we'll use that, but let's focus here, right? So now let's say we want to, for that figure that you see, let me draw that figure here for simplicity. So you have some inputs, and you have a dot product here, and then you have a sigmoid transformation, and then you have output, right? Now there is W1, W2, W3, W4 that we are trying to estimate, and each Wi, if we need to learn them, we need to do gradient descent with respect to each of these W's. So there is a partial derivative we have to do with respect to each Wi for this loss function. And this loss function is defined as E, right? So partial derivative of E with respect to this weight is equal to, what is the derivative of this square function? We are taking a partial derivative with respect to W. What is the derivative of x squared? 2x, okay? So let's do 2x. This is our TD minus OD, right? Is that it? What else we have to do? Chain rule, right? Then we have to do x, whatever this x is, we have to take a derivative of that x as well. So what is the derivative? So we are essentially looking at derivative of this and derivative of this. What is the derivative of TD with respect to Wi? 0. Why?
There's no W, it's just a label.
Is that just the label? There is no W. It doesn't depend on W. It's a constant, right? That's 0. What is, so all that you need to know, compute is minus derivative of OD, partial derivative of OD with respect to Wi. Right? Is this clear? Right? Okay. This half and 2 goes away. That's why we actually had that half. That helps. But now we have something like this, and we need to know how to compute this. So OD is like essentially this sigmoid function, right? So what do we do? What can we do? We cannot apply the formula that we learned directly, because that formula was sigma x with d dx of with respect to x. But here we have two different things, right? In other words, OD is not sigma of W, it's sigma of something else. What do we do in that case?
Chain rule again?
Chain rule. But we know net D is a function of W. So we kind of break it down into two terms. We have learned in calculus that we can do net D and then times net D, which depends on W. Why we want to do this? Because OD is a sigmoid of net D. So this part now, we can apply our previously learned formula of this, the derivative of the sigmoid function, because you have with respect to the same variable, you are taking the derivative of the sigmoid of that variable. But now you have an additional term here that you also need to take care of. And what did we define for net D? What is net D actually? What is the definition of net D? Net D is what?
Sum of Wi xi.
Sum of W, it's the dot product. It's the dot product. Good. Right? Yeah. Okay. So this is the sum of Wi xi. Okay, now it looks good. What is the derivative of the summation of Wi xi with respect to Wi? And let's say this goes over j, so Wj xj. What is this partial derivative? What is the value? So W1 x1, the dot product, W2 x2, Wk xk. We are taking a derivative with respect to, let's say, W3. What is the output? Sum of all the x?
No, just that.
Just x3, right? So others are 0. It's constant. So with respect to Wi, if I take the derivative, it's just xi. Is this clear? Okay. Now, what about this part? We already know what this is. What is that? Derivative of the sigmoid function, right? Which is sigmoid times 1 minus sigmoid, right? So we'll just take the minus sign here, and then sigmoid of net D times 1 minus sigmoid of net D. Times xi. Yeah, it looks bad, but yeah. Right? But what is sigmoid of net D? The sigmoid of net D. Net D is dot product. What is the definition of sigmoid of net D? What variable does it represent? That's OD. That's your prediction. So this is just OD. And this is just 1 minus OD. Right? Yeah. So if I do this, it's essentially TD minus OD, then OD times 1 minus OD times xi. Looks good. Easy to remember. Right? When I was in my undergrad, I used to have this formula, like, oh, everybody was like before the exam, TD minus OD, OD into 1 minus OD into XI. Okay? That's how exams are in our country. You have to memorize everything. And you have to just dump it out. So, essentially, the derivative, and then you, of course, you have this sum over all the examples, right? Because we are doing this for all examples in the training data set. But the point is, in the output layer, the gradient with respect to Wi is essentially, and with respect to one particular D, the stochastic version of the gradient descent, is essentially the label minus your prediction times 1 minus the prediction times the input. Okay? What does this really mean? This means you have, let's say, 4 inputs, x1, x2, x3, x4, and you have a dot product here, then you have a sigmoid here, and this. So the dot product is your net D, and the output is your sigmoid of net D, and the weights you have is W1, W2, W3, and W4. So what we are essentially saying is, if you want to compute the loss here, and you want to update these weights, so the gradient with respect to W1 is going to be whatever your x is, the big X you are sending, the label of that minus this output for that label times this output times 1 minus this output times this x1. Now, when it comes to delta E with respect to W2, then you will do the same. This part remains the same for the same D. This part remains the same. Just this changes. So you multiply with x2 now. And then you do all these computations, and you get a gradient with respect to the whole W, which is essentially a gradient of E with respect to W1, E, W2, and so on. Now you get a direction to move forward. But we still have a problem. What is that? Are we done? Because we already learned how to update the weight W, because once you have this, what is your formula to update W? The way you update W is essentially use the gradient descent, right? So Wi at t plus 1 time iteration is essentially Wi at t minus step function, step size, learning rate, and your this, the gradient with respect to W, I, right? What is still missing? Can we just do gradient descent right now? Look at that network.
We still need back propagation.
We still need back propagation, right? So far, what we have done can only give us these weights in the last layer. But we don't know what's going to happen here. Why this is a problem? Because here you know, in the output layer, you knew what the output should be. And based on that, you could compute the error. But what is the error here? Can you compute what kind of error happened at this node? Do we know that? Can we do something about it? That is what backpropagation people did. That is where the algorithm is coming from. It's not easy. That got them a Turing Award. But now if you look at the formulation, it's really easy. Can we assume something and hope it works? Okay, what is a logical, plain English ChatGPT output or like ChatGPT style explanation of what kind of error do we see here? What can you say about this? Just from your pre-trained language model. You know what errors happened here. You see that. And based on that, you can compute gradients and you know how to update these weights. But then you need to backpropagate and you don't know what kind of errors happened here. Can we try to connect what error happened here and what error we see here? Can we try to estimate what kind of error happened here based on the kind of error that we see here? Ideas? Okay, let's take this node. And we know what kind of error happened here. What do you think? Who contributed to these errors? Whatever error that happened. Yes?
All the nodes still have.
To the left,
Yeah.
all nodes, right? But there are, so we are talking about ages as well, right?
Right.
So do we consider all the ages?
All the, wait, so that's the word again, all the what?
All the weights contributed to the error here?
Well, they contribute in different quantities.
Okay, so think about this. The node that connects this and this age, does that add anything to the error here?
Oh, I see. No, we don't care about all the edges.
No. Yeah. Or think about this node connecting to this node, right? Does this age, does it add anything here? No. Only we need to care about those ages that are connected to the previous layer with this node. Right? Next, we also know what these ages are, right? What the weights of these ages were. So we kind of know a weighted combination or linear combination of the output at this node with respect to all these nodes. So can we assume, because the output here is a linear combination and then a sigmoid transformation, also the error that we see here is also a linear combination of errors that I see everywhere here. In other words, can I assume whatever error happened here is actually should be backpropagated from all the errors that connects to that particular node? Because this node, whatever error it had in total, have kind of distributed those errors in these output layers with those weights. This is the assumption that is made by backpropagation algorithm. So the point is, we don't know what error actually happened here, but we'll just assume all the nodes that connect to the subsequent layer, all the ages that connects to the subsequent layer. So we know what happened, what errors happened in the subsequent layer. So we can backpropagate those errors to each of these nodes based on their connections and their weights. It's a linear combination of the weights of the errors that actually happened in the subsequent layer. Once you make that assumption, then you have an estimate of error. And once you have an error function, then you can do gradient descent. Right? So this is what you will do. Remember, in the output layer, our delta k, now this delta, let's define delta first. This is important. This delta, you remember that formula, right? TD minus OD, OD times 1 minus OD times x. So it's a term multiplied by the input x. So the whole term is called the delta, the error. The TD minus OD, OD times 1 minus OD, the whole thing is the delta. That's how it's defined with some input. This is the error term. And now we are trying to approximate that error for other layers. So in the output layer, the error is again the same. OK, 1 minus OK, Tk minus OK. But when it comes to hidden layer, the first part will still remain the same because this is what comes from wire. The sigmoid function derivative, right? Remember? Sigmoid of this, 1 minus sigmoid of this. That part will remain the same. But what will change is, now you take a linear combination, weighted combination of all the error that happened in the output layer and take a linear combination of that to approximate what error happened rather than looking at Tk minus OK, because there is no Tk minus OK there. You just take a linear combination of the errors here, 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 multiplied. The linear combination comes from the weights of these edges. That gives you an approximation of the error. You can do the same thing in the subsequent layers. Now this layer becomes your output layer. This layer becomes your hidden layer. And this layer becomes your input layer. And keep going until you hit the input layer. That's the formula that you have to use. So if that's the output layer, you have a formula. If you have a hidden layer, you have this formula. And then you update all the weights in the network and keep doing this until your accuracy on the validation set drops to a certain degree. Then you stop your training and hope it will do good in your testing and whatever goal task you have. I'll stop here. There are some announcements. So next class will be the last lecture on Tuesday. I'm not going to have a lecture on Thursday. I think I can cover everything by the next class. And in the next class, please bring your laptops. We'll do some exercise. I'm not going to tell you exactly what, but we'll do something. It will be fun. It's not something stressful. And what else? If you are, because we are now stopping, I'll kind of, the assignment on neural networks are supposed to go out next week, but I'll just release them as soon as possible, maybe by today or tomorrow. If you feel like start working, you can, if you want. And the neural network thing will not have a programming assignment. It will mostly be conceptual. But I want to give some bonus chances to people who think you might benefit from it. And one way is there is some annotation task that we need volunteers. So that is something where you can chime in and give your task. That is one assignment I can give. The other one could be more technical, where there is a backpropagation implementation of neural networks. So you don't have to do it, but then if you feel like that gives you a bonus point, that helps you with your midterm. I'm not deciding right now where I'm going to add it. So all I can say is I will try to use it in a way that maximizes your grade. Okay? So these 2 bonus points will come in. I could supplement in your midterm grade using that. I could also supplement your assignments in some way. So those bonus point assignments will be also discussed in the next class. And yeah, I think that's it. Yeah, go ahead.
Could you post these slides on Canvas?
I haven't? Okay, I'll do that. Yeah, I'll do it right after this class. And if you're struggling with the project still, please talk to me in my office hour. I most of the time sit down and nobody comes. Right? So, all right. See you then.